This is video number 4 for sections 7.3 and 11.2, operations on complex numbers. This is definitely a side topic. We won't make a huge deal out of this, but having just introduced complex numbers, we want to make the point now that they are numbers. They can be added, subtracted, multiplied, and divided. Those of you that are going on to take trigonometry, you will meet complex numbers again in that course. Let's run through each type of problem here, and each time we want to end up with an answer that looks like a plus bi. That's what a complex number looks like. All right, starting with adding. Hopefully when you look at this problem and even the one underneath it, your brain is telling you this looks awfully similar to things we've done before, in particular combining like terms, and that's really all there is to it. This first example is particularly easy because these parentheses aren't doing anything. From a mathematical standpoint, if I drop them, nothing really changes. And as soon as I do, I realize that what I have here is just some like terms. I have a couple of the terms that are just numbers, and I have a couple of the terms with the i's. We'll just combine them. I have 4 take away 2, which is 2. I have 7i minus 8i, which makes minus I. That's it. That's the answer. 2 minus I is the sum of those two complex numbers. Notice it fits the pattern a plus bi. In this case, a would be 2, b would be negative 1. 2 plus negative 1i, which simplifies to 2 minus I. Almost the same thing in the second example. Of course, with subtraction, I just have to be careful. That minus there needs to be distributed to both parts. So let's take care of that first. The first guy is fine, but then when I distribute, I get minus 4 and then plus 5i. After that, it's just combine the like terms. I've got a negative 6 and a negative 4 for negative 10. I've got a negative 3i and a positive 5i. For positive 2i. Once again, my final answer is in the form a plus bi. So adding and subtracting complex numbers is very, very simple. Let's move on now to multiplication. And before I do that example, I do need to point out one key fact here. I, remember the definition of I, the square root of negative 1. Well, what would I squared be equal to? It's pretty simple. Squaring a square root simply makes the square root disappear. That means I squared must be negative 1. Keep that in mind as we go through our example. All right, so here's my problem. I've got these two complex numbers. I'm interested in multiplying them together. Again, I hope this looks very familiar to you. It's very related to something we've been doing recently, namely FOIL problems. It looks just like a FOIL problem. Well, that's exactly how you approach it. Just do your FOIL. Let's see. 3 times negative 2 would be negative 6. My outer would be 3 times 5i. That's positive 15i. My inner, negative 4i times negative 2 would be plus 8i. And my last looks like negative 20i squared. Negative 4 times 5 is negative 20, and I times I would be I squared. Now, when I go to clean this up, I have to remember a couple of things. Obviously, I'm going to be on the lookout for like terms. I see that I've got a couple right here. But also, my final answer needs to look like a plus bi. There's no I squareds allowed in these final answers. That's where our key fact comes in. I squared is just equal to negative 1. So when I go to simplify here, I've got the negative 6, 15i and 8i make 23i, and then I squared can be replaced with negative 1. Well, that means that term at the end simply becomes plus 20, which means it's now a like term with the first term. Negative 6 plus 20 is 14 plus the 23i, and I'm done. I have to have a final answer that looks like a plus bi. Finally, let's move on to the division. and this is perhaps the trickiest situation here. In this problem, I'm dividing 2 plus 3i by 1 plus 2i. What am I supposed to do here? Well, I'm supposed to work this out in some way so that the final answer looks like this, a plus bi. Notice there's no I anywhere in a denominator in these answers. So what I'm going to try to do is take a step that will rid me of this I down here in the denominator. It turns out there's a trick involved. The trick is called multiply by the conjugate. The conjugate means take a look at the complex number you have on the bottom. The conjugate is the exact same thing, but with the sign opposite in the middle. In other words, the conjugate of 1 plus 2i is 1 minus 2i. I'm going to take this fraction, this division problem, and I'm going to multiply the bottom by 1 minus 2i. Now, the only way I can do that is if I also multiply the top times 1 minus 2i. You say, where are you getting this from? How is this going to help? Well, notice that what I've done is I've just created now two FOIL problems, one on the top, one on the bottom. The one on the bottom fits the a plus b, a minus b pattern, and that's the key. That's why we're picking the conjugate. Watch what happens now when we multiply. I'll go ahead and start with the bottom. If I start FOILing this out, I get 1 times 1. The outer term is minus 2i. The inner term is plus 2i. See how those are going to wipe out? The back part is minus 4i squared. Well, see, the middle two guys are going to cancel out. That'll happen every time because of the a plus b, a minus b pattern. The I squared is going to turn into a negative 1, which means I'm not going to have an I in the denominator anymore. Let's go ahead and fill in the top part of the FOIL problem. I've got 2 times 1, which is 2. I've got minus 4i from the outer, plus 3i for the inner, and minus 6i squared for the last. Let's go ahead and simplify now. On the top, I have 2. I've got a couple of like terms, minus I. Remember that I squared is just a negative 1. On the bottom, I've got the 1. The middle terms drop out. Once again, the I squared is just a negative 1. Let's see. On the top now, 2 minus I, that's going to become plus 6. And 1 plus 4. So now I've got 8 minus I up top and 5 on the bottom. I'm just about done. The computer is going to be a little picky with you on this. They really want you to type it in the form a plus bi. So the last thing I need to do is distribute this 5 into both parts. And I end up with 8/5 for the first part minus 1/5. There's an understood 1 right next to that I. 1/5 I. Now this fits the pattern a plus bi. This is the answer to that division problem. The trick of multiplying by the conjugate of the denominator works every time for these division problems.